Hi everybody, welcome back to my channel on Feynman integration. Today we're going to be developing a new way to represent the factorial as an integral. You guys are all familiar with this one, I'm sure, that n factorial is equal to the integral from 0 to infinity of x to the n e to the negative x dx. That's fairly well known, but we're going to be developing a different one. And I'm also going to be kind of walking through the process of how you would figure this out if that was your goal from the start. If you wanted to get a factorial somewhere out of the process of performing Feynman integration, which involves derivatives, how would you do it? Well, the factorial is this plus 2 forever and ever and ever. I'm sorry, it actually, sorry, that's incorrect. It's more proper to write it like this: n minus 1 n minus 2 times 2 times 1, like that. Well, how are we going to get that out of taking derivatives? Well, I know. If you take things like x to the n and just start taking derivatives with respect to x, you can see you'll the first iteration you'll recover in n by bringing that exponent down. This will change to an n minus 1. Take another derivative, you'll get back the n minus 1. This will change to an n minus 2. Take another derivative, you get back an n minus 2. This will become an n minus 3, and you get the picture. So there we go. We want something of that form to come out during our process of Feynman integration. Well, okay. But actually, a better one to do would be this. Maybe x to the negative n. And the reason I say that is so that we can start with n and start counting up. So we know how many derivatives we need to take in order to reach a certain desired factorial. And I'll show you why. So if you take a derivative with respect to x of that, in our first iteration, you'll recover a negative n. Then this will become negative quantity n plus 1. Take another derivative and you'll get back a negative n plus 1. Then a negative n plus 2. And so on and so on and so on. And you can see that this will be alternating, but that's not that big a deal. We still get to start at n and then start counting up, which is what we want to do. Okay, so somehow that has to come out of a definite integral. It has to come out of an integral in, we need to get basically x, we need to get, well, here, I'll show you. This needs to happen. From A to B, and somehow this has to somehow equal something of the form like 1 over t, just as a guess, because that way if we anti-differentiate this with respect to t, we can also anti-differentiate this with respect to t. So I hope I'm making sense so far. But how are you going to get a 1 over t by, what are you going to have to evaluate between a and b, and what are a and b going to have to be in order to get a 1 over t? Well, we know this t with respect to x is constant, so this will have to be the result of, well, I'll show you. We could get it this way. of course. That's obvious. If you evaluated that, you would get 1 over t minus 0 over t, which would give you 1 over t. But how are we going to just get this x over t as the result of an antiderivative? Well, we could just we could just differentiate this with respect to x and get a function purely in terms of t, but that's not good because this would just be f of t dx. We don't want that. Okay, oh, well, how about this? There we go. And now we have an excuse as to why we got that t on the bottom and where it came from. And if we plug in 0, if we plug in 1 for x, we still get 1 over t. And if we plug in 0, we still get 0. All right. So this is the antiderivative of this with respect to x. So all we have to do is differentiate this with respect to x, and we find our function of x and t, and it will be this. It will be x. Sorry. If we differentiate this, because this is the antiderivative, if we differentiate x to the t over t with respect to x, we will get x to the t minus 1. All right? If we anti-differentiated that, we'd get x to the t over t, and that's exactly what we have. But I don't want to start like that. I don't want to start with x to the t minus 1 as our original integral. I don't know why, although it would work, and you could definitely recover a factorial from there, but I don't know, I just don't like that. So we know it would still basically work if we did, let's just see what happens if we try x to the t. That's going to be our function. We're going to pick this as our function with one modification. It's not going to be t minus 1, it's just going to be t. All right. So we figured out what we need our function to look like more or less in order to be able to recover factorials during the process of Feynman integration. So we have some function of t being equal to the integral from 0 to 1 of x to the t dx. We also know that this is equal to x to the t plus 1 over t plus 1 evaluated from 0 to 1. And that is equal to 1 over t plus 1 minus 0 over t plus 1. So it's just this. So the two things we're interested in really are these two things. Those two things are equal. All right. Well, if they're equal, their derivatives are equal. So we can say that f prime of t is equal to the derivative of with respect to t of this, which you can get by using the Leibniz rule for differentiation under the integral sign by taking a partial with respect to t of the integrand. Okay. Keep the same bounds. What is the derivative with respect to t of x to the t? With respect to t, it is, of course, you'll get back x to the t, then you'll get natural log x dx. And I'm just going to try to squeeze this in here. This is equal to t plus 1 to the negative 1. And that's how we're going to be writing. That's how we're going to be expressing that, because it'll make it easier. All right. So we took a derivative with respect to this, so it must be equal to the derivative with respect to t of this. So this is going to be equal to negative 1 times t plus 1 to the negative 2. So now we've got it. We're going to get back a factorial out of this if we just keep taking derivatives. So let's do it. We'll take 3 or 4. So f double prime of t is equal to the integral from 0 to 1 of x to the t natural log squared x dx. I hope you can see where that comes from. This is when we differentiate with respect to t, this is a constant, it stays. We get back the x to the t, that's right there, plus we get another ln x. That's represented by that squared right there. And this is going to be equal to, let's see, negative 2 times negative 1 is just 2 times t plus 1 to the negative 3. Let's keep going. F triple prime t equals integral 0 to 1 of x to the t natural log cubed x dx, which is in turn equal to negative 6 t plus 1 to the negative 4. Okay, that's enough to see the pattern. So let's write that down in general in terms of n. So we can say that the nth derivative of our function of t is equal to the integral from 0 to 1 of, well, the x to the t never changes, so that's just going to stay x to the t. All right, but this ln x, the power on the ln x is changing, and it is precisely equal to the whatever derivative. If we're taking the third derivative, if we're on our third derivative, it will be equal to 3. If we're on our second, it will be equal to 2. If we're on our nth, it will be equal to n. Natural log to the nth power of x dx, and this is equal to, all right, well, it's alternating. We can see we have a negative, positive, negative, so it's definitely going to be negative 1 to, well, let's see, is it n or is it n plus 1? Okay, so on our first derivative, which is n, we get a negative. And so that means it's just going to be negative 1 to the n, because on our second derivative, our n would become 2, and we would square the negative 1, which would make it a positive. On our third derivative, this would become 3, which would cube it, bringing it back to a negative. So that's what we want. That's how it's going to start. And then the t plus 1 inside the parentheses never changes, but the power on it does, and the power is always a negative power. Let's see, on our first derivative we have 2, on our second we have 3, on our third we have 4, so clearly this is n plus 1. All right. We're forgetting something though. Oh yeah, the whole point of this, which is the factorial. Okay, didn't leave myself enough room here. We'll just put it down here. No, that's stupid. Well, what's it going to be anyway? Okay, so our first derivative is 1 factorial, our second is 2, our third is 3. So it's just going to perfectly match up with whatever derivative we're on. So this is times n factorial. I know that's terrible. It should all be written on one line. Sorry about that. But I'll rewrite it down here. Basically, this is going to be what we know. So far, we know that some integral from 0 to 1 of x to the t natural log to the nx dx is going to be equal to -1 to the n times n factorial times t plus 1 to the negative n plus 1. There we go. Now it's just algebra and we have our n factorial. So let's do the algebra. We'll start with our n factorial. All right. Well, that's going to be equal to, let's see, what do we want to write first? Well, if we divide both sides by -1 to the n, we're still going to get -1 to the n on the other side. Because -1 to the negative n, well, this is either going to be equal to -1 or 1, and if you take its reciprocal, it's going to be the same thing. So we're still going to be left with -1 to the n. All right. What does this become? Well, you take its reciprocal, it just gets rid of that negative side. So this is just going to be t plus 1 to the n plus 1 power. And what do we have left? Of course, we have the integral. 0 to 1 of x to the t natural log to the n x dx. Okay. Well, those t's are annoying, aren't they? All right. Well, how can we get rid of them? We'll just plug in a number. Let's say this is going to be true for all t. This will be true for all values of t. Am I correct in saying that, though? Yeah. What about 0? You can plug in 0 for t, and it's not going to mess anything up. Because the integral from 0 to 1 of dx is just going to be, x value is just going to be 1, and that's going to be equal to 1. Yeah, 0 should work. So, n factorial should be equal to -1 to the n times 1 times the integral from 0 to 1 of natural log to the nx dx. There we go. New integral representation of the factorial. Hope you enjoyed that.